All right, and just making a note that homework number 8 on derivatives in electric circuits is posted. Okay, we're going to spend all of today working on that. We should get most, if not all the way through it. Okay, so you can get a roll on this. And of course, homework 7, MATLAB homework 7, both due tomorrow. I do not believe there will be MATLAB homework posted because looking at the schedule, MATLAB supplemental, yes, coming up next week, week of 10/21, right? So we don't do both in the same week. Okay. So, moving forward. I think last time we tried to make the point that in electric circuits and devices, the most basic quantities, voltage, right, is a derivative of energy, dW dq, with respect to electric charge. Current, right, we said that's the rate of flow of charge, so that's dq dt, that's a derivative. Power, energy per unit time, dW dt, all these basic physical definitions in circuits are derivatives. So we want to start out by just getting some more practice in calculating some of these. And the first example is really more like a physics 2 type example. Okay, and let's say, for example, that we have an electric charge Q of t. Okay, and let's say it's 1 divided by 50, okay, times the sine of 250 pi times time. Okay, so a sinusoidal electric charge. Okay, and so this is the charge right here. Okay, and anybody recall what are the units of electric charge? Yeah, that's coulombs. Okay, so we'll put a C right here. Okay, and let's say that we've got a voltage, V of t, okay, given by 100 times the sine, and we'll have the same frequency, 250 pi times time. Okay, I would like to find a number of different things based on the definitions. So part A, let's see if we can calculate the current, right? And the current would be I of t, by definition, flow of electric charge. That is the derivative dq dt. Okay, and so that's the first thing. Next thing I want will be B, that's going to be the power. Okay, and the power, P of t, we had written this down as a chain rule before, right? dW dq times dq dt. Turns out that is just voltage times current, right? So we want the voltage V of t multiplied by the current I of t. Okay, and then as an engineer, once I have the power, I might be interested in the maximum value, right? The maximum value of the power. Okay, and that could be a quantity that I would use some calculus in order to figure out where the power might be a maximum, but only if I have to. All right, if I can understand something about the function, may or may not require calculus to answer that question. Okay. Any questions on where we're going here before we move ahead? All right, so again, if you have not had calculus prior, please have the sheet out, the derivative sheet. Okay, and in fact, even on the back, one thing we'll see shortly today, we'll get into this product rule, one of the rules on the back side, and so we'll see some use of that in some examples. All right, so first of all, the current, part A. All right, I of t is the derivative dq dt, so I'm going to take the derivative with respect to time of the charge function. I've got 1 over 50 times the sine, right, of 250 pi times t. So help me out. I of t. What do I do with the 1 over 50 out in front? Stays there, right? I've got a constant times a function. The constant stays out front. So I've got 1 over 50. And now I need the derivative of a sine function. Okay? And so the question is, do we know the derivative of a sine? According to the sheet, if I've got sine omega t, where omega could be any number, angular frequency, then what's the derivative of sine omega t? The omega comes out front, and then it's cosine omega t. So in this case, what's the omega? It's the 250 times pi, right? The omega is whatever number is in front of the t. Okay, so according to this, the 1 over 50 stays out front. The 250 pi comes out front. And then the sine, that derivative becomes a cosine. Cosine of 250 pi times t. Questions on how we did that derivative before we move forward? All right, so can I simplify this at all? Yeah, I can factor out, right, the 250 divided by 50. I'm going to get the number 5. So I got 5 times pi, and it's a cosine, 250 pi t. Just reiterating, in an engineering classroom, you will frequently see it written just like this. No parentheses. Okay, whenever you see a sine or cosine without parentheses, we will do that when the t is the last argument of the function. It's just shorthand. Okay, but you certainly can't be wrong for being more exact in doing that. Okay, cosine 250 pi t. What are the units on this? Yeah, amps, right? So if I start with charge in base units of coulombs, okay, and this one, my bad, got to put the units on here. This is volts. Then I'm going to get current in amps. Okay. All right, so part B. What is the power? V times I. So I want the power, P of t, right, voltage multiplied by current. Okay, and so that should be pretty straightforward since I've got both of these things now. The voltage is 100 times the sine, 250 pi t. All right, and the current just calculated, all right, so we've got voltage here. Current is 5 pi, all right, times the cosine 250 pi t. Can I simplify that at all? The 100 times the 5, right? It's going to give me 500 pi, and I can get rid of some of these parentheses. I'm going to have 500 pi times the sine of 250 pi t times the cosine of 250 pi t. What are the units on power? It's going to be watts, right? So everything in base units. I'll get the answer here in base units. Great. Okay, so we didn't do any calculus there, right? No derivative. We just took the current that we had calculated, multiplied by the given voltage. How about this guy? Maximum power. Do I need calculus in order to figure out the maximum power here? Say that again? Unless you have a graphing calculator. Graphing calculator could work, right? So in general, right, if I have a plot of a function, then the maximum value, I can see what it is, right? If I got a function that does whatever, right? The idea is calculus can tell me where the flat spot is, right? And so I can find maximums that way. So one option is to do some calculus here, try and find a flat spot. Do I have to do calculus to find a flat spot on a function like this one? Say again? Isn't it just the amplitude? So that's a good question, right? Because so, let's suppose I didn't have the cosine here. If I didn't have the cosine, I'd have 500 pi times the sine, and then clearly the maximum value of that would just be the amplitude. But here's the problem. The sine is a maximum at what angle? Forget the cosine. The sine is a maximum at what angle? Pi over 2 radians, right? So I could solve for the time, right? It would be 250 pi t equals pi over 2, whatever that is in time. So the place where the sine is a maximum is the place where the cosine is what? 0. Okay? So the whole idea that I'm just going to use this amplitude doesn't really follow, right? Because this amplitude would be if I only had the sine, but when this thing's maximum, that one's 0. Okay? So where do these things combine equally in terms of angle? Right, so leading question here. Sine is maximum at pi over 2. Cosine is maximum where? 0. Yeah, so, you know, split the difference in between, right? 45 degrees is where you get the equal contribution. Okay, but, you know, is there anything I can do from a trigonometry standpoint? Because I could use calculus, right? If I wanted to use calculus to find a maximum, what would I do with this function? I'd take a derivative, right? So I take the derivative of this. Now the problem is I got a sine multiplied by a cosine. All right, so that's not itself one of the simplified forms on the sheet. You know, in fact, we would have to use what's called the product rule, which we're going to get to shortly here today, to say I've got one function multiplied by another. How do I do the derivative? So if you start playing that forward in your mind, when I start taking derivatives of sines and cosines, what do I get? I get more sines and cosines. Okay, so I could do some calculus on this, but it's just going to give me more sines and cosines, and then I'm just going to have to start doing some trigonometry at some point. So here's a hint for you. If you have a calculus problem that has trigonometry, usually it's in your best interest to do what you can do with the trigonometry first before you decide if you need to use any calculus. Okay? Because when I start taking derivatives of trig functions, I just get more trig functions, I just get more trigonometry. So, can I do something with trigonometry right here to simplify this guy before I even think about taking a derivative?
Obviously this sine plus cosine rule is not good, or... Oh wait, what? What did I just say?
Thoughts?
Wait.
Can I simplify sine of theta times cosine theta? Right, this is the theta. It's the same theta here, right? This is why I've got an opportunity. If this was different theta, not so easy. Okay? Same theta, I ought to be able to do something here.
Wait. Could it be 250 pi t equals sine times cosine? Or am I thinking in the wrong direction?
So you took the angle out and said that equaled sine times cosine.
Well, I completely forgot how to do this, which is weird.
Okay, so how's this? Is there a trig identity that's got sine multiplied by cosine? Yes? Not quite. Okay, sine squared plus cosine squared equals 1. You guys got the trig sheet, right? The trig sheet is somewhere in your notes. Isn't there something on the trig sheet that says I get a sine of theta times a cosine of theta?
I know there's a sine divided by cosine, but obviously it doesn't help.
Sine divided by cosine is what? That's tangent. That's true.
Double angle.
Double angle. Tell me what the double angle is.
Sine of 2x equals 2 sine x cosine x.
All right, so the sine of 2 theta, right, is 2 times the sine of theta times the cosine of theta. So the other way of looking at that is the sine of theta times the cosine of theta would be what? Here, we'll write this one down, what you just said, right? The sine of 2 theta is 2 times the sine of theta times the cosine of theta, right? That's what you just said. So what I've got here is a sine of theta times the cosine of theta. So can't I isolate this part and say, doesn't this mean that the sine 2 theta times the cosine 2 theta would be what? Sorry, sine theta, cosine theta, not 2. Sine theta, cosine theta would be what? Yeah, it'd be the sine of 2 theta divided by 2, right? So what do we have here? What's theta? I got 250 pi, right? Times t. All right, all of that is the theta. So here's sine theta, here's cosine theta. Can't I replace that with the sine of twice that value divided by 2? So if that's true, then can't I say that the power, again, just manipulating the trig, I got the 500 pi out front still, and I'm going to replace that sine theta cosine theta, where theta is this whole thing, 250 pi t. All right, I'm going to take that, right, and replace it with the sine of 2 theta. So 500 pi, right? So I'm going to get the sine of 2 theta, 500 pi t, but I got to divide it by 2, right? You guys with me? So I recognize I have a sine times a cosine of the same angle, therefore I can apply this half angle formula. Okay, and so power, I can cancel out the 2. I'm going to get 250 pi times the sine 500 pi t. Interesting. Okay, that's also in watts. So now, this expression looks quite a bit simpler than this one. All right, this one's got a sine multiplied by a cosine. This one only has a sine with a different frequency. Do I need calculus to get the max power? Got a yes over here and a no over there. What do you think? Amplitude. All right, I don't care what the frequency is. Sine function oscillates between what two numbers? 1 and minus 1. Does not matter what the argument is, right? 1 and minus 1 is the sine function. The number out in front is the maximum. Okay, so no calculus required for this one. P max, okay, is equal to 250 pi watts. Okay, that's it. Incidentally, a sine function, it's kind of an aside here, but a sine function looks like this, right? So the maximum occurs still where the flat spot is, right? So it's not that I can't use calculus. If I use calculus to find the maximum here,
it'd probably take a lot longer, maybe.
Well, I need to do the process. I need to take the derivative. What's the derivative of the sine function? Cosine function. I got to figure out then, where's the flat spot? It's where the derivative equals what? 0. So the question becomes, where's the cosine 0? Well, the cosine is 0 at the same locations, right? This angle is pi over 2, right? So the same location that I can see the maximum here, I know from trig that the cosine is 0. Okay, so the lesson here is taking derivatives, setting them equal to 0 when you have trigonometry. You still need to have the same basic knowledge of trigonometry to answer that next question. Okay, and so usually calculus doesn't buy you a whole lot, right? Because you still need to have the knowledge of the sine and cosine function. If you have that knowledge, well then you know the maximum of the sine occurs when theta is pi over 2, and you're done. You guys with me? Okay, so once again, just an example of trigonometry is pervasive, right? It's all over the place. Physics, vectors, statics, dynamics, circuits. So if trig, something you still need work on after the exam number 1, we have trig littered through derivatives, integrals, differential equations all the way through. Keep working on your trig, and the math department will have you continue to work on your trig when you take Calc 1 and Calc 2 and Calc 3, okay? And differential equations. Great. Questions on this before we move forward? All right, so now I want to get to some circuit elements, kind of like we talked about with the complex numbers. We're going to look at capacitors and inductors. So we talked a lot about complex impedances and how we added those up. These guys get really interesting when I start having circuits that I'm building that have inductors and capacitors. Okay, those devices are actually used in order to control input-output relationships between voltage and current. And it turns out those relationships are all derivatives. Okay, and so this is the reason I can use a circuit to design an input or an output that I want. Okay, so this example is going to be about current and voltage, okay, in an inductor. Okay, Okay, and so here's a general behavior of an inductor. Okay, an inductor again is the coil, looks like a mechanical kind of spring almost. Okay, it has an inductance L, and I can have a voltage across the inductor, voltage as a function of time. Okay, and of course the current would be flowing through the wire and the inductor, I of t. Okay, and so turns out that the governing law here is the following. The voltage drop across an inductor, okay, is actually related to the derivative of the current. And the relationship is L times di dt. Okay, and so this is, the basic way that an inductor works. Okay, and so what it means is that if I have an inductor in a circuit and I'm controlling one or the other, the voltage or the current, I can control the slope of what the current is doing by changing the voltage source. Okay. Similarly, if I change the current in a purposeful way, so I control the rate of change, that will control the voltage that I get across. Right? So you can start stacking together these circuit components and you can make a circuit do what you want it to do. Okay. All right, so given this, let's answer this question. Okay. Let's say, given L is equal to 100 millihenries, okay? And let me give you an equation for the current. I of t is equal to t times e to the minus 3t amps. So it's a linear function t times a decaying exponential, e to the minus 3t. Okay, here's what I want to find. Number one, can we find the voltage, okay, which is V of t. Okay, and then here will be an interesting one. What would be the value of the current, okay, at the time when the voltage is 0? Okay, so why in the world would I care what the value of the current is when the voltage is 0? Like if you're out, messing around at the power plant and you see a sign that says 0 voltage. Is that scary? Do I care when things have 0 voltage?
If I put my health on the line, then I would be concerned.
So is your health on the line if you're at a point in time where the voltage is 0?
Oh, if it's just 0, okay, never mind.
No, it's a question, right?
If it was much higher, then I would be concerned. Otherwise, I wouldn't be.
It's not the voltage that kills you as a response here. What kills you? The current kills you.
That's right, but you need voltage in order to have current.
Do you? Do you need voltage in order to have current?
Yes.
Yeah.
It's a linear relation.
Right, so question was, aren't they directly proportional? Well, if I have a resistor, I've got V equals IR. They're directly proportional there, linearly proportional, right? Here I've got an inductor. I got V equals L di dt. Not the same as V equals IR, right? So, I heard some appropriate rumblings from over here. So, when the voltage is 0, what does that tell me about the current? How about right here? When the voltage is 0, what does that equation literally tell me about the current? Does it mean the current 0? It means that the slope of the current is 0, right? If the slope of the current is 0, then the current is what? Max or min. Okay, so in fact, right at the point in time where I have no voltage could very well be the most dangerous point. Okay? Now, if you have no voltage all the time, V equals 0 is a constant, okay? Well, then you're not worried, right? But V equals 0 at one instant in time, maximum current. All right, excellent. So, moving forward, how do I get the voltage? Okay, well, apparently, V of t is equal to L times the derivative, di dt. So I know what the L is. L is 100 millihenries. How many henries is that? 0.1. Not a bad idea to just write things in base units right away. Right? If I write things in base units right away, then my answer will come out for V in what? Volts. Okay, so keep the units right. So 0.100, okay, times di dt. So what I need to do here is I need to find di dt and then multiply by 0.1. So let's do that. So di dt is the derivative with respect to time of the current. The current was given, it's t e to the minus 3t. So, pulling out the sheet here. Do I see t e to the minus 3t on the front side here? I got some of it right. I've got a e to the st. I've got a t to any power, right? In this case, my t is a t to the first power. Okay, but the problem here is these two guys are multiplied together. Right, so I don't have a simplified formula, right, on the front of the sheet that says what do I do when I have t multiplied by e to the st. So I'm going to need something else. Okay, and so this is the one thing, and again, all the formulas on the back side, right, this is photocopied out of the calculus book. Okay, the formulas on the back, you're going to spend time deriving these, using a lot of these in calculus class. The one that pops up all over the place, that it kind of limits your ability to do problems if you don't have it, is this one. Okay, it's called the product rule. Got to have the product rule. Okay, and so if you look at back side of the sheet, number 5, these derivatives are all written as f of x. They do a lot of f of x's in the math books, right? But it's the same idea, right? So it says, number 5, the derivative of f of x times g of x. And they got written down f of x times a g prime of x and g times f prime. Math departments use prime. Okay, we do this in engineering as well. When the context is appropriate. We use a prime to mean shorthand for take the derivative. Okay? So apparently I got to do some things with the functions. I got to take some derivatives. Okay, let me write this out for a function of time. Okay, and so this is kind of an aside, but I'm going to need this guy, the product rule. Okay, and what the product rule says is that if I take the derivative of two functions that are multiplied together, let's say I've got f of t, and I multiply by g of t, okay? Then I got to do something with these functions, okay? And so the way I like to remember it is it's the first function multiplied by the derivative of the second, and then it's the second multiplied by the derivative of the first, okay? But if you listen to what I just said there, it doesn't matter which order or way you do that, okay? You take one, you multiply it by the derivative of the other, and then you do it again with the other one, okay, and that's it. So it's going to be, in this case, right, it's going to be f of t multiplied by the derivative of g, dg dt, right, plus the other function, g of t, multiplied by the derivative of f, df dt. Okay, and so you can do this, you can derive this straight from the definition of the derivative, right, the limit as delta t approaches 0, change in y divided by change in time. That kind of derivation may or may not go through that in calc class. You can find it in a calculus book. Okay, but it's a really useful rule in order to be able to take these derivatives. So, here, what's the f and what's the g? Yeah, so it looks like f of t, one function, is just the function t. Okay, and by the way, you get to decide what these are. Right? And depending upon how it's written here, there might be more than one option for the way to write this down. In this case, I can't see really any other option. It's a t all by itself, so that's one of the functions. Okay, and the g of t is the other function, which is e to the minus 3t. So your plan with this product rule is to identify an f and a g that are themselves just simple cases on the front of the sheet here, right? Because if I get f and g that I know the derivatives here, then I can apply the rule and I'm good to go. Questions on the plan here before we move forward? So my approach, first times derivative of the second, plus the second times the derivative of the first, that's what we're going to try here. Okay, so let's do it. So di dt, first function, that's going to be the function t, times the derivative of the second. So I'll write this out kind of longhand here. The derivative of e to the minus 3t. All right. Plus, I got to add the second function here, which is e to the minus 3t, all right, times the derivative of the first function, ddt of t. Okay, again, when you start getting the hang of these using the product rule, I don't need to see this long hand step, right? You just do those derivatives as you go. All right, so continuing up here then. Okay, then di dt, let's see if we can do these derivatives. I got the t out front. What's the derivative of e to the minus 3t? This guy right here. So if you're trying to figure out where this comes from, right, this is a special case on the sheet. This is an e to the st. The s would be what number? Negative 3. Okay, so if it's e to the st, the s will come down times e to the st again. Incidentally, the exponential function is the only function that when I take its derivative, I get the same thing again. Right? And that's pretty useful. In fact, that's the entire key to solving differential equations. Okay? And so remember that a few weeks from now when we get into differential equations, the fact that e to the st, when I take its derivative, I get itself back again, it means e to the st is the solution to an awful lot of problems. Okay, any kind of problem where I need a function and I need to add it to derivatives of itself and get 0, right? I got to get the same thing, so I have like terms. Okay, so this is an important property. E to the st, I get the same thing. So t times this, I get the same thing, but I get the constant in front. So minus 3, right, e to the minus 3t. So this is first derivative of the second, plus the second function, e to the minus 3t. What's the derivative of t? Is it 0? 1. It's t to the first power, right? So again, when in doubt, remember what it is. It's the slope of the line, y equals t, right? That line has a slope of 1. Okay, so great. Thing about the product rule, you start with one term, two things multiplied, and because the rule has a plus in it, it always gets one level more complicated now, right? Because now I have two terms instead of one. Okay, and so usually at this point you got to think about doing some algebra on it. Can I do any algebra to simplify some things here? What was that? Multiply the t. Okay, so I know that I can, this can be a minus 3t. I was thinking more, instead of multiplying things through, can I factor anything out? Yeah, I can factor out an e to the minus 3t here because it's in both terms. So I'm going to write e to the minus 3t out front. And what am I going to have left? This is minus 3t here. And this is what? Plus 1. Okay, anytime you factor something out, right, you can always check it by distributing back through. Okay, so this one times that is the first term, minus 3t e to the minus 3t. And then the last term is just an e to the minus 3t. Great, that's di dt. Okay, or if this minus sign bothers you here, you can write this as di dt is e to the minus 3t, and this is 1 minus 3t. Okay, either way you want to write it. All right, so am I done yet? The question is, what am I trying to get? Yeah, I want the voltage, which is 0.1 times di dt. Okay, and so finally the voltage, V of t, I got to multiply by 0.1. 0.100 e to the minus 3t, 1 minus 3t. What would the units be on that? Units would be volts. What if I wanted the units to be millivolts? How would I write that? It'd be times 1,000, right? But if it's 0.100 volts, that's the same as how many millivolts? It'd be 100, right? 1, 2, 3 on the decimal place. Okay, so again, get used to bouncing around between amps, milliamps, millivolts, microcoulombs. In circuits, we do things on big scales, right? We got capacitors measured in microfarads, right? And we're putting them inside a circuit that's got a resistor measured in ohms. So we got things that occur over all these different orders of magnitude, which affects what are the labels I use on my axis scales and things, right? And if you screw that up, you could be talking about the difference between milliamps and amps, right? And what's the difference to you if you grab a hold of the wire and it either has milliamps or amps? Yeah, life or death. Okay, so pretty important in circuits to get your units down and your orders of magnitude straightened out. Okay, but this way, if you leave everything in base units, right, this is just going to be volts over here at the end. All right, so we got the voltage. Okay, and the question now is, what's the value of the current when the voltage is equal to 0? And we want to know that. Why? Yeah, current when V of t is equal to 0. If I find that place, that means that the slope of the current is 0, which means the current is probably a what? Maybe a max, could be a min. It's a flat spot, okay? All right, so let's do that. So how do I find the voltage equals 0? I got the voltage, what do I do with it? Set it equal to 0, okay? So 0.100 e to the minus 3t, and I've got 1 minus 3t, and this whole thing is supposed to be 0. Is that a difficult equation to solve? So, general approach here. Any kind of an equation where you're trying to solve for the roots, right? Roots as a general term means values of the independent variable t when I get 0, right? That's the roots. So if I plotted this function, the roots would be what? If I look at it, the roots would be what? How would I tell by looking at the plot where a root is? Say again? Where it crosses the x-axis, right? I could see where the roots are, okay? Now, in general, that is possible anytime I can line things up on one side of the equation and have it equal 0. When I say line things up, I mean have things multiplied together, right? This is the entire basis for factoring, like in a polynomial. T minus 3, t minus 7, I think we did last time, right? Either one of those is a possibility. So take a look at this function. Do I got more than one function multiplied there? So the strategy is to find the places where this is 0. I got to think about every one of these things that's multiplied. If any one of them is 0, then that's an answer, right? All right, so how about this first part? 0.1 e to the minus 3t. Is that ever 0? No? Why is that never 0? E to any power is some number. What was the answer here?
It would never reach 0.
So you got to have some understanding of what the function does, right? So it's a decaying exponential. At t equals 0, it starts where? This is e to the 0.
E to the 0 is 1.
E to the 0 is 1, right? Any number to the 0, 1. Okay, and so great. So I know that time starts at 0, so this is starting at 1. It's a positive number. Is this thing ever going to be a negative number? No, there's no negative sign in front. So I'm taking a positive, putting positive values of time. The negative here means 1 over e to that exponent. All right, so 1 over e to any exponent is a small number, right? But the number approaches what? 0, never crosses 0. Okay, so the point is, just by knowing some things about the function, this is never 0. Okay, and so, boy, this is not a very complicated root to find. This has to be when 1 minus 3t equals 0, right? The only other possibility, and that happens when t equals 1/3 of a second. Okay, very good. Okay, now, t equals 1/3 of a second is a place where I've got a flat spot. That's all that calculus tells me, right? So I've got, you know, flat spot right here. Flat spot on I of t. Okay, so we got all these tools in calculus to figure out, is the flat spot a maximum? Is the flat spot a minimum? What are some of those tools? I could do a second derivative, right? And I could look for the value of the concavity, concave up, concave down. But I start to look at these functions that have product rules in them, right? And what happens is, now I take the derivative, and now I got another product. So the next derivative is even messier, right? And I got to evaluate that function. So, you know, use the tools of calculus when you need them and recognize when you don't. Okay, that's a big part of being an engineer, right? Recognize when you need to throw everything but the kitchen sink at a problem, and recognize when you don't. Okay, and so how many flat spots do I have here? I got only one flat spot, right? Do I know where it is? It's at 1/3 of a second. So thinking about I of t, this is it right here. Where does it start? It starts, right, at a value of, at t equals 0? 0. So I know it starts at 0. I know there's only one flat spot. Do I know the value of the current at the flat spot? I got to find it, right? I evaluated at 1/3 is what I want, right? So I of 1/3, I of t is t, e to the minus 3t. So it's 1/3 e to the minus 3 times 1/3. So this is the same. It's kind of weird looking, but is this not the same as 1/3e? Who can compute 1/3e on their calculator? What was that? 0.121. Can I get corroboration on that? 121. I didn't quite get 121. Anybody else? 123. That's the number I had. 123. Again, anybody have trouble computing this? Right, this is e to the minus 1, right? So you just do an exponential of -1 and you divide that by 3. Okay?
Sorry to forget, where did the value of e even come from? I know where pi comes from, but for e, is that difficult to explain?
No, I mean, you know, who here can take a crack at that? What is e?
Isn't it like the slope, or e is the number where its slope is the same, like its derivative is just itself?
Well, that's true. I like that explanation from a calculus standpoint. Okay, but it is, you know, fundamentally, what is e? What if I said, yeah, go ahead.
Isn't it like 1 plus 1/x versus dx? Like
Well, so there's a expansion, right? Turns out that continuous functions in general, you take more math and you'll see this. You can do expansions of functions in terms of infinite series that are equal to functions. So you can explain it from a series standpoint. What's the other, you know, where do you use an e in pre-calculus? Natural log. What does an e have to do with natural log? It's the inverse natural log, sort of, right? So if I say the natural log of 3, or better yet, the natural log of e is 1. That's the definition of e. Right? E is the base of the natural log function. So it's the exponent that you raise e to in order to get e, right, is what? Is 1. So the natural log of e is 1. Okay?
And one other thing I'm wondering, I noticed that for both E and pi, the decimal places basically go on forever.
Yeah, correct.
No repetition at all.
Yep.
Are there more numbers that do that?
Yes, and in fact, if you guys really like math, okay, this is where math becomes interesting just from the pure math standpoint, all right? If you really like math, then you gotta go take some, you can get a math minor, right? Engineering, you got 5 or 6 math classes required. You take a few more, you get a math minor. If you take more math, what you realize is, once you get past all the math that engineers use, the names of the math courses start to go backwards, right? So like a really advanced math class for a math major is called algebra. Right? Seriously. And they go up like this, and you get all the way up to like graduate level. They take classes, in fact, advanced undergrad. They take classes like real variables. You know, it's a real number. Seriously? That's a graduate level math class. But in a class like that is where you do things like prove that there's an infinite number of irrational numbers between any 2 rational numbers. So you said, are there more numbers like that? Not only is there more, there's an infinite number. Okay, and there was a time when I was a graduate student that I could almost do that proof. Okay, but we have plenty of people in the math department that could whip that out in a minute. Okay, but the point is, yeah, I mean, a number that just repeats forever, decimals, those are called irrational numbers. They're all over the place. Infinite number of them. Yes?
How did you get the 3 times 1/3? Negative 3?
Yeah, so this is the function right here I'm evaluating, right? So I of t is t e to the minus 3t. So I'm trying to find the value of I at the flat spot. So I evaluated it at the flat spot. So I of 1/3, this is 1/3 e to the minus 3t. This 1/3 is the t value that I substituted in.
I know, but how do you make that positive?
How did I do this? So this is, the 3 cancels the 3. So this becomes e to the minus 1. And e to the minus 1 is the same as 1 over e. So 1 over e is here, and I just put the 1/3. Are you with me? Or you could, you know, you don't need to write it as that. I mean, I of 1/3, the other way to look at it as this is 1/3 e to the minus 1. Just write it like that. So you can do this on your calculator, right? It's exp of minus 1, and then you divide it by 3. Everybody with me here?
Yeah.
We good?
I am now.
You are now? Yes? Good? All right, so the number is 0.123. What are the units on that? Amps. 0.123 amps. Good. All right, so what if I want to sketch this? Right? I of t is equal to t e to the minus 3t. Okay, so keep in mind that one of the nice things about calculus, right, is it enables you to quickly sketch functions, right? If you wouldn't have any calculus and you were just in algebra class and I said pull out a piece of paper and sketch that, okay, the method you would have to use, it would be like the, let me make a table of numbers and start guessing. I'll start at 0 and figure out what the numbers are. You miss all the action, right, if you're not on the right scale when you start guessing. Okay, you do a little bit of calculus and you know where the action is. The action's at 1/3. So if that's true, and I'm going to sketch this, whenever you sketch a function, you got to put some tick marks on. General rule of thumb, you want about how many tick marks? 4, 5, 6, whatever, some single digit reasonable number. Suggestion for tick marks?
Thirds.
Yeah, thirds, right? I know the action's at 1/3. Why not use thirds? 0, 1/3, 2/3, 3/3, 4/3, 5/3, 6/3, okay? So we'll just use thirds. Okay, so I know I've got action at 1/3. I know that this is t over here in seconds, right? I know that 3/3 is the same as what? 1, and 6/3 is the same as what? 2. Okay, so there we go. We go between up to 2 seconds with intervals of thirds here. Okay, and then I'm going to need some things on the y-axis. Function starts where? Yeah, t equals 0. The function starts here. I know I got a flat spot at what value of time? What value of time? 1/3. So I'm going to have to put a dot somewhere here, right? And you know, the question I started asking before is, how do I know if this is a max or min? Do I have to go do concave up, concave down, all of this business? How about this for deductive logic? Function starts here. Flat spot over here. Is the flat spot above or below the axis? It's above. It's 0.123, right? So I got a number here. Are there any more flat spots? No. So if I plug one more number on the other side, right, then it's, the puzzle is solved, right? All right, so we can plug numbers on the other side. And in fact, since I have the tick marks, we can see what they are. But plug in some numbers here at, values of t. I know I started here at 0. So when t is 0, I'm at 0. All right, we know when I'm at a third, we already have the answer, 0.123 amps. How about 1 second? Yeah, at 1 second, I of t, let's just use the function, right? T, e to the minus 3. So this is going to be t, 1, e to the minus 3. What's e to the minus 3? Give me a decimal, somebody. Zero point what? 0.49? 50? 0.050, that's 2 digits. 2 digits good enough for a hand graph. All right, so I'm at 0.05. So I go from 0.12, I'm below it now. 0.05, is this going to be a max or min? It's a max. It's a flat spot. The number to the right of it goes down. What happens as the numbers keep going? What about 2? This is t, which is 2, right? E to the what? Minus 3 times 2 is minus 6. What's 2 times e to the minus 6? Run that number, somebody. 0.005. It's a whole order of magnitude less, right? 1/10 of the one before. Great. So, suggestions for tick marks. Should I do 0.005 for tick marks? How many tick marks would I need to get up to 0.123?
Oh, gosh.
So I want a few tick marks. Give me a suggestion here. 0.025? I could do that. Sure, I could do that. Or even just 0.05. That would just give me 3 maybe. Right, 0.05, 0.1, right, 0.15. We could do 0.25. I like that answer. 1, how many tick marks would I need then? Yeah, 1, 2, 3, 4, 5. If I do that, then my max is way up here. Okay, this thing goes up in a hurry. So this is 0.025, right? And this one up here is what? 0.125. This value is 0.123, right? It's almost there. All right, and so this is I of t right here, and this is in amps. By the way, if I want to label that in milliamps, then this would be what? 25, and that would be 125. In fact, that's the way you would probably want to label this. Okay, so I'm right here, I'm in amps, and so we got some numbers. So at 1, I'm at 0.05, which is right here, right? So at 1, I'm at the second tick mark right here, and at 2, I'm at 0.005, which is about how far the way up here? 1/5, 20% of the way up. Pretty much down here to the bottom, right? So you can see what this function does. All right, this function comes all the way up, hits a flat spot, and then it comes all the way down. And what happens like as the time keeps increasing? It's an exponential decay, right? It never crosses the axis. Okay, so flat spot is right here. It's a maximum. I didn't need a second derivative to tell me that. Okay, sometimes you need a second derivative to tell you that, sometimes you don't. Questions? Don't grab the wire. Don't grab the wire at 1/3 of a second, right, is the rule. Okay, although 0.125 amps, probably be okay. It would hurt. It would hurt. All right, great. So sketching functions, product rule, all important stuff for calculus. Okay, let's keep going here. Current and voltage in an inductor. Let's go now and visit the same kind of problem we did with velocity acceleration. Remember the warning I gave you last time? One of your exam problems is going to be nothing but sketching, right? Sketching functions that have no equation. Okay, and so let's take a look at one of these. So let's say, for example, I do a direct current, okay, across an inductor. Okay, and so this is my voltage as a function of time. And then I'm going to have a current I of t, okay, across this inductor L. Okay, and here's what I'm going to do. I'm just going to make that voltage source a 9-volt battery. Every 2 seconds, I'm going to switch the terminals. Okay, so we'll go out to 8 seconds here. Right, so this is 2, 4, 6, 8. This is time over here in seconds. Okay, and this is going to be the voltage V of t in volts. 0 right here, and we'll just go plus or minus 9 volts. So for the first 2 seconds, we're going to connect it to the positive. Then we're going to switch it and go down here to the negative. Then after 2 seconds, we'll come back up to the positive. And then after 2 seconds, we'll switch it back down to the negative. Okay, like that. Incidentally, what kind of a signal do we call that, do you think? Yeah, this is called a square wave. Okay, and so what I'm interested in is if I do a square wave for a voltage, okay, which again, you can think of this sort of like an alternating electricity problem, right? Alternating current in the wall is what kind of function? Sinusoidal, right? Frequency is 60 hertz. Okay, and so I've got a sinusoidal. In this case, this isn't sinusoidal, it's, you know, squareusoidal, square wave. But we use these, right? We can generate signals like this with a signal analyzer, okay, with a signal generator. Okay, and so, so I generate the square wave. The question is, you know, what is going to be the current and also the power? Okay, so what I want to do is I want to plot I of t and also P of t, and remember what the power is. The power is the voltage multiplied by the current. So we want to think about how do I multiply two graphs that don't even have an equation? Okay, because that's what we're going to do. Plot I of t and P of t. Okay, and of course we're going to need a number for the L. Let's say the L is 500 millihenries. If L is equal to 500 millihenries. All right, so this is relatively straightforward because it's just a repeating function. If I can figure out what happens, for example, in the first 4 seconds, is it hard to finish the problem? No, it's periodic, so it's just going to do it over again. Okay, this assumes I get back to where I started. Okay, so let's think about this solution for a minute. So what would the solution be? Okay, well, first of all, you got to recall the relationship, right? I've got V of t is equal to L times di dt. Okay, and I've got an L value. So V of t is equal to 500 millihenries. If I want to put that in base units, that'd be how many henries? 0.500 henries, right, times di dt. Now, what I want to plot here is the first thing is I want to plot the I, right? This is a statement about how the voltage relates to what? The derivative of I, which graphically speaking is what? It's the slope of I. So maybe rewrite it so you can say, so what's the slope of I then? di dt. If I solve for di dt, what do I get? It'd be 1 over 0.500 times the voltage, right? 1 over 0.5 is the same as what? 2, right? 2 times the voltage. Okay, so this is a statement, okay, not a bad idea whenever you're doing a piece of math and you have an inkling to what it means but you can't exactly wrap your arms around it. Write the words out, okay? Literally the words of what this means. The words for this is the slope of the current, right? By definition, that's this. Slope of the current, the equal sign is the word is, okay? the slope of the current is, what does this say in words? Twice the voltage. Okay, so that's the mathematical statement. Twice the voltage. Okay, now, what about the voltage? Do I know the number? All right, so, since V of t, okay, is equal to plus or minus 9 volts in every interval, it's either plus or minus, right? What kind of function is the number plus 9? So if I look at this function, I want to characterize it. What kind of function is that? It's a horizontal line, which is a constant, right? This is constant, okay, and I'll make the note here that it's alternating, right? But if I look at any other, any particular interval, it's a constant, plus 9 for the first 2 seconds, minus 9 for the next 2 seconds, okay? And so if that's true, if V of t is constant, okay, and the slope of the current is twice whatever that constant is, then what kind of function is the current? Yeah, the current is linear, right? Do I know what the slope of the line is? So the word says the slope of the line is what? 18. It's twice the voltage. Is linear with a slope of plus or minus 18. Right? Does it bother anybody that I'm doing both intervals at once? All right, we can look at the first interval, and it's just the pluses, right? So voltage is 9. It's a constant. That means I is linear with a slope of plus 18. Second interval, V is minus 9 is a constant. I is linear with a slope of minus 18. Right? And then when I get back to this point, it's the same argument again, right? All right, so how do I get these words then onto paper in terms of what this plot would look like? So I'm going to have I of t. All right, I've got to have tick marks on the x that look the same as the original. So 2, 4, 6, and 8. Okay, and this is t over here in seconds. Okay, and I of t, if I put everything in base units over here, I got volts, right? Then I of t would have units of what? Yeah, amps. Okay, and so we ought to be able to start drawing this. So for the first interval between 0 and 2, V is 9, constant. The current I of t is linear. Slope is positive 18. So you should be explicitly told this, but we're assuming we're starting with nothing here at t equals 0. So if I start at 0, then if the slope is 18, and after 2 seconds, how high am I going to be? 36. Okay, so we can just come up here and say, hey, this is 36. And so it's a line, so, that's it. Right? And the slope has to be 18. So, again, that's the first interval, 0 to 2. I've got positive 9. Next interval, 2 to 4, V is negative 9 now. I of t is a straight line with a slope of negative 18. What do you think? Yeah. Slope of negative 18 for the same amount of time is going to put me back at 0. Okay? So, same idea. Slope now is minus 18. So if I'm now back to 0 again, and I'm at this point in time, and I apply the same square wave, what happens? It's just the same thing again, right? So apparently then, if I apply a square wave to a voltage, okay, across an inductor, then I of t, what kind of wave would we call that? Is that a sawtooth? Yeah, I'd call this one a triangle wave. Okay, so I start with the square wave for voltage. This is if I have an inductor. Okay, that gives me a triangle wave for the current. All right, and then I want to plot here the power now. All right, so this is the power. In fact, we'll just label it P of t. And units on power is what? Watts. Power in watts. Okay, great. So, P is supposed to be V multiplied by I. How in the world do I multiply a square wave times a triangle wave? Okay, so at any point in time, the two numbers need to multiply. So that's true. I can take any points on there and multiply the two numbers at any time. Because this function is discontinuous, right? It has jumps, right? That one's got some corners. Maybe not a bad idea to think about, let's multiply this interval first. Okay, and then we'll move to the next one, right? And if we can get that understood, then we can just repeat it for the next two. So that would be my plan. Okay, so let's think about this. I've got the two plots now. What do we want to do to plot the power? So the power, by definition, P of t is going to be the voltage V of t times I of t. What if I just write this as P of t? Let's just put a number in here for what the voltage does. Isn't this the voltage? Plus or minus 9. So the power is going to be plus or minus 9, right, times whatever the current is. And the plus or minus basically means in the first 2 seconds it's a plus, right, because this is plus. In the second 2 seconds it's a minus, and then I repeat that again. So, say again? 2v squared? You lost me there. Explain where you're going with that.
That's going to be the power of the maximum. Your slope.
Well, I mean, literally what it is it's plus or minus 9 times whatever the current is, right? So, what kind of function is I of t? Is it constant, linear, quadratic? What is it? Linear in any interval. If I multiply a line by a number, what do I get? I get another line, right?
Yeah.
So P of t is going to be lines, but keep in mind, when I go to the next interval, the line's probably not going to keep going because I got to switch the sign from plus to minus, right? So one interval at a time. Take the first interval, okay? I'm going to take this line and multiply it by number 9. When I go to the next interval, I'm going to take this line and multiply it by the number -9. So apparently the power on this thing is going to be plus and minus values, right? So when I come out here, I'm going to need to deal with plus and minus. So the tick marks on the x-axis are going to be the same. 2, 4, 6, 8. All right, so I've got t over here in seconds, right? But in the first 2 seconds here, what should be my tick marks on the y-axis? So literally, I'm asking you this, at t is equal to 2, what's the value of the power? So I got a value of 36 here. I got to multiply that by 9, right? 9 times 36, somebody run that. 324. Okay, now, that is right up until I hit 2. As soon as I cross 2, the number becomes what? Negative what, though? 324, right? I take this next line, and I multiply it by a negative number. The 0 point stays where? What's 0 times any number? Still 0. So it just takes this value and flips it down here, right? Scales the axis. So I'm going to go start at 0, up to 324 in the first interval. Next interval, apparently I'm going to drop straight down here to minus 324. All right, and so just to the right here, I've got to take the second line, multiply it by -9. Okay, and so it takes this line, drops it straight down, and of course 0 still stays at 0, right? So this line does this. Now, I'm back to where I started, right here, back at 0. Current does the same thing as the first interval. Voltage does the same thing as the first intervals. And so the rest of the curve will look like what? It's just going to repeat, right? But take a look what happens. If this repeats, you know, and this thing's got the same slope here and here, right, then this line is just going to keep going, right? So if I got my tick marks squared away appropriately here, the slope has just got to stay the same. Make the dot bigger, okay, like that. And then this thing's going to drop down again, and then it'll go back up like that. Okay, so this should be a straight line all the way through like that. Okay, that function is what we call what? Yeah, this guy is the sawtooth wave. Okay, so this is the basic behavior, right? If I start with a square wave for a voltage, grab a 9-volt battery, plus and minus to the terminals every 2 seconds, I will get a triangle wave for the current. And then if I look at the power, I'll actually get the sawtooth wave for the power. Okay, and of course, this is if I have an inductor. Okay, if I put something else here, resistor, capacitor, whatever, this behavior doesn't happen. All right, so these are the fundamentals of circuits. Different circuit devices change the input-output relationship based on things like derivative relationships. Okay. Question over here.
I have a question.
Yep.
Just to get like why is the drop? Why did it drop straight down?
Yeah, why it drops straight down here? So what I'm doing is saying that by definition the power is the voltage times the current. So in the first interval, I've got a voltage of +9, the graph behind me. So I just take the current graph, which is this line, and I multiply it by 9. That gives me this. Now as soon as I'm between 2 and 4, I know what the current is, it looks like that. And the answer for the power is the voltage times this line. Well, if I look at the voltage between 2 and 4, the voltage is now a negative number. So I need to take this line and multiply this line by a negative number. The easiest way to multiply a line by a negative number is to take the two endpoints of the line, multiply those two numbers, and connect the dots. Right? So if I take this number, multiply by -9, it gives me -324. And if I take 0 and multiply by -9, it still gives me 0. So now I have the new line. Okay, so the line in the second interval is this line multiplied by -9. So I could get the equation of the line, right? I mean, you can see by looking at it. Somebody tell me, what's the equation of the line in the second interval? I of t equals y equals mx plus b. The m is what? -18. What's the b? What's the b? 72. Right? Here's the thing. This is an important result. The equations of the lines here, not that helpful to me. They're all different. Right? Because the y-intercept moves. Every time I scooch over, the y-intercept moves. So there are times when we want to use calculus where the equations, honestly, are more trouble than they're worth. I don't want piecewise equations for every one of these lines. I want to understand what to do with them, which is to use the slope to draw the next one. Right? Very good. All right, so not quite done with electricity. Got 3-4 minutes left in the lecture. I want to at least talk a little about capacitors so you can get ahead on the homework. By the way, we'll have plenty of time to wrap this up and beam deflections next week, the other application. Okay, but let me at least introduce what happens now if I have a capacitor. Okay, because you'll have a few homework problems with this. So the next example current and voltage in a capacitor. Okay, and here's the short of it. From a circuit standpoint, behavior of a capacitor is kind of like the opposite, okay, from a mathematical standpoint of the behavior of an inductor. Okay, in the following way. A capacitor, if I have a voltage applied across, V of t, and I have a current flowing through, I of t, when we had the inductor, right, we had V equals L di dt. So the voltage controlled the slope of the current. Here, it's exactly the opposite. The current controls the slope of the voltage. Okay, and so the governing law for this guy is I of t is actually C times the derivative dV dt. So now, think about if I start building a circuit and I'm controlling one or the other, voltage or current. If I put in an inductor in there, right, V equals L di dt, I can control the rate of change of the current by controlling the voltage source, or if I'm controlling the current myself, I'm changing the voltage with a rate of change of the current. If the same circuit has capacitors in it, then look what happens. I can control the value of the current that flows by purposely changing the voltage, or I can control the current source. And if I do that, that will control then the slope of the voltage. So this is the same thing, the same kind of things we just did here, except the interpretation's reversed. So I've got a couple more good examples on this, and I'll go ahead and work them in full on Tuesday. But this is enough information to start on the homework on this, okay? Homework due next Friday. And we'll wrap this up, and then we'll get into beam deflections. Beam deflections next week.